Okay, everyone, so we have our exam 3 coming up 1 week from today in class, and we are going to finish all the new material today and even get out probably a little early. So we'll have plenty of time to study for this. And right now what you have online Kappa to do is the last homework assignment covering chapter 40 here, Inference for Logistic Regression, and how to build confidence intervals for the slopes in the log odds model here. And you also have a practice test online Kappa that you can do multiple times. That's basically a old exam 3 converted to a practice test that with randomized problems. So each time you click on it, you'll get new variation. That's very helpful. And then I'm going to put up another old exam for you, a practice exam. So what we're going to do next time is review for the exam. All right, so let's everybody turn to page 130, chapter 40, Inference for Logistic Regression. All right, so let's just look at the title here. Inference for Logistic Regression, chi-square tests, z-tests, and confidence intervals. So basically, we're going to be using a slightly modified chi-square test for the overall effect of the overall collective effect of all the slopes in the model to see in the log odds model, that's linear. We're looking if there's any of these predictor variables are significant, just like we did for linear regression. And then if we get if this overall effect is significant, then we'll see which one of these slopes, maybe all of them, are significant. And we're going to use z-tests for the individual slopes, and then we're going to build confidence intervals around them. So that's the idea. All right, so as I say here, the null hypothesis is the usual one for the collective effect of all the slopes. That is, all the betas here are 0. So that means there's nothing going on in this model. And we might as well just predict the overall, might as well just look, remember this is a 0-1 variable that we're predicting with logistic regression. In this case, whether or not somebody gets into medical school. And so if all these are 0, then we're just going to basically use the percentage of people who got into medical school in our sample as the best estimate for the probability of the percentage of people who will get in general, and it won't, in the population, and it won't depend on our predictor variables, which in this case are gender, whether you're male or female changes your chances of getting in, and your biological science score. All right. And then the alternative hypothesis is the same as before, that at least one of these, there's something in this model, at least one of these slopes, one of these predictor variables tells us some information, gives us some information about whether or not people get into med school. Okay, so that's the idea. Now, in ordinary regression, remember we used either a chi-square test if we had a large enough sample, or an f-test, and for the overall effect. In logistic regression, we're just going to be using, we'll never use an f-test because we're predicting counts. And think back to why we use an f-test or why we use a t-test. We're not going to be using a t-test for the individual slopes, or we're not going to be using an f-test for the collective effect of all the slopes, because we use t-tests and f-tests when we don't know the standard deviation of the population, and we're using our sample standard deviation to make a prediction about that. But here we have counts, and like we do for a chi-square test, counts, and we estimate, you can estimate the standard deviation from the count itself. You don't need a separate estimate. you know, like when you have quantitative data, right? And let's say we want to estimate final exam scores or heights or any type of quantitative data. You have a mean and you have a standard deviation, and they're not linked to each other, right? They're separate. You could have, the mean doesn't tell you anything about the standard deviation. But with counts, the mean and the standard deviation are linked. If you know that 60%, 60 out of 100, or however many, 60% of the people got into med school, then you also know in your sample, so if your mean is 60.6, then you know your standard deviation is what? The square root of 0.6 times 0.4. The square root of point, it's p, the percentage, times 1 minus p, and then you take the square root of that. So, so we're not estimating a separate, we don't have a separate standard deviation that, that's a bad estimate of our, we have too small a sample and it's a bad estimate. That's when we used, that's why we use a t-test or a f-test, is when we, because you, the mean itself gives us information about the standard deviation. I mean, you never use an f-test for percentage data, right? Or you never use a t-test. Okay. So, and then the degrees of freedom are the number of parameters in the model minus 1, the same way it is usually with our chi-square test in the past. So it's the number of predictor variables. The number of parameters in our model, for example, here's our model. If this was our model right here, the degrees of freedom are going to be the number of betas minus the intercept, which is always the same as the number of predictor variables. So that's what I'm saying here. Okay? And it's the same for both types of regression. All right, and then to test the individual slopes, in ordinary regression, we used either a z-test or a t-test. You know, if we had a small sample, we used a t-test. But in logistic regression, we always use a z-test or a chi-square test, or a likelihood version of that. Okay, so let's look at this output right now for this example where we're trying to predict acceptance to medical school based on whether somebody's male or female in their biological science score. And here's the output for the chi-square test. And here's the output for sort of the ANOVA version. The ANOVA, instead of having the sum of squares error, we have something called the deviance. So we're looking at, you know, we're splitting up we're partitioning the deviance into a model and an error here. Maybe this is time right now to just look at this difference between the main, just turn the page, and let's look at this main difference between ordinary and logistic regression. I've been talking about this a lot, and let's just read this carefully together. Okay? The main difference is how we estimate these parameters, these betas. Instead of minimizing the sum of the squared errors, the sum of the squared residuals, your actual y values minus your predicted y values, those are the squaring those, and trying to minimize the sum of those squared errors, we estimate it by choosing the betas that maximize the likelihood of getting the sample data we did. So maximizing this likelihood is the same as minimizing the deviance. And the deviance is -2 times the log of the likelihood. Now, if you want to look at the mathematics of this, and it's really not hard, I suggest that you read it's on our course website, and I'm just trying to remember exactly. Read lessons 12 and 13. This is just optional. This is totally optional if you want to know more about it. So you could read that. on our course website under the R independent study. In go.illinois.edu, and instead of, you could go to /stat200, or you could just go to stat390. And lessons 12 and 13 explain it, and goes along with what we've been learning. So if you're in the R independent study, this is this week's homework, and we explain it in more detail. Okay, so in other words, the idea is that minimizing the deviance in logistic regression is analogous to minimizing the sum of squared errors in ordinary regression. So deviance plays the same role in logistic regression as the sum of squares in ordinary regression. And if you look at that analysis of deviance table on the previous page, and note its similarity to the ANOVA table that we have. And if you look at this R squared here, it's very similar to if you squared R here. It's going to give you extremely similar results. And if you had the bigger the sample size, the closer these R squareds will get to each other, and the closer the p-values will get to each other. And in the limit, they'll be the same. Okay? So, so now you're probably wondering why we do this likelihood procedure. And, well, if we have continuous predictor variables like we do in logistic regression, predicting a 0-1 outcome, each point has its own value of x, right, and a result of either 0 or 1. And it's a continuous x-axis, and you either get 0 or 1. So that means that if you get a 0 or 1, then you either get into med school, you get a 1, or a 0, you don't. So when you take the odds, that would be 0 over 1, or 1 over 0, and then the log odds, you're going to get either negative infinity to positive infinity, right? So you can't really minimize the squared error for the predicted logs. Minimizing the squared error would be minimizing a bunch of infinities. That doesn't even, it's not going to work. So what you do instead is you bin them, you lump them together, right? So that the zeros and ones, you have a bunch of zeros and ones, and then with about the same x, you make an interval, and that will give us percentages instead of zeros or ones, right? It will give us percentages. And it will give finite log odds, but then the fitting results depend on how we make those intervals, and sometimes we don't even have enough data. We have to make quite large intervals. So so then you could try to minimize that. You could try to take those percentages, those intervals, and that would give parameters, so you take the, you minimize the sum of the observed minus, in each interval, you take your percentage, your observed percentage minus a predicted percentage. You could do that. But that would only do a good job of fitting in the range where p is near, in the middle, or near 0.5. But it would not be sensitive to the prediction. It wouldn't give realistic odds for more rare events. So maximum likelihood is sensitive to those rare events and picks parameters that work throughout the range of our data and not just in the middle. That's the short, intuitive argument. And if you want to read the more mathematical argument, you can read that. But that's the idea. Okay, so as a result, we get this deviance table here, but we are going to just use, in this modified chi-square. Okay, so let's look at how to interpret this. And so we have this fitted model. First of all, we're looking at these. Here's our fitted model. We're looking at these slopes right here. And we get this model. And then to test the overall model significance, we do this chi-square test. And the null is the usual. The null is what? that in this case, both are two slopes. These, both the gender slope and the biological science slope are 0 in the population. Okay? So both betas, both of these two, betas meaning in the population, are equal to 0. And our alternative is what? That at least one of them is not. That means either the gender or the biological science, or both of them are not 0. So at least one beta is not equal to 0. That's it. And that's pretty. And then you look at, let's look at what we get here. We can look at this chi-squared right here. And then we're going to get, and then compare this chi-squared to the critical value at some significance level, or else we could just compute a p-value for it here. So we got, so our chi-square stat is huge. Do you know that's huge? Because we have 2 degrees of freedom, remember? So degrees of freedom are equal to the number of parameters minus 1. So let's just remember, this is just a review of what we always do, the number of parameters minus 1. We have 1, 2, 3 parameters. The number of parameters is all those betas minus 1. That's the number of slopes in our model. Okay, and when the null is true, we're testing the null, when the null is true, how likely is it to get that big a chi-square statistic? Remember, when the null is true, we'd expect what? We'd expect a chi-square value equal to the degrees of freedom, which would be equal to 2. And we got one that's so much bigger than that. So we'd expect it to look like, whoa, I'm going to make a huge long tail. We'd expect, remember, chi-square, this is the distribution of the chi-square statistic when the null's true, when nothing's going on, when gender makes no difference, and when biological science makes no difference. You'd expect to get, here's 0, this is our chi-square curve with 2 degrees of freedom, and it's going to be shaped, it's not going to be shaped like the normal yet, it's going to go down like this, but remember, it never crosses. So this keeps getting smaller and smaller and smaller and smaller and smaller and smaller and smaller, and we'd expect a value around 2 right there, but instead we've got this one way, way, way out here. So the probability that that would happen by the luck of the draw is tiny. So our chi-square statistic is what? We got a chi-square here of, what is it here? 29? 29, that's huge, 29.33. And this p-value that's given here, this p-value, this right here, this tiny little p-value is that little dot. And what do I have here? What do I have written down there? Right here, that's 2. That's a chi-square of 2. That's about, it's a chi-square. That's because that's the degrees of freedom. So you'd expect about here, but it's way down there. Okay? And the critical value, do you remember the critical value for rejecting the null? Like 5% in the tail is about 6. So 2, 4, 6, this, so about here, 2, 4, 6, about here, I think it was 5.99. Remember that kept coming up for chi-square with 2 degrees of freedom. That's the critical value for 5%. 5.99. That means all the way to here, all that would be, from here on in would be 5%, excuse me. From here all the way down there would be 5%. So that would be, call this would be 5%. And this is a tiny, tiny, tiny fraction of that. Does that make sense to people? I know the picture is not the best, but you understand. Do you understand? It's just far, way, the probability of getting this, if this model was just completely, if those slopes were 0, is tiny. And doesn't that make sense? Because what we're saying is, what would be, the biological science wouldn't make any difference, your score on that. And of course it makes some difference. I mean, that's what the MCAT, that's probably the most important part of the MCAT. So it's kind of a silly thing to test. So what's our conclusion? That at least one of these two slopes, we're going to go with the alternative, at least one of them is not equal to 0. And then when we look here, then we're going to test the individual ones. Once we see this, look, they both turn out to be significant. All right? Well, let's say we didn't have that. Let's say we didn't know that. So to test whether the individual slopes are significant, we're going to do these z-tests. And let's state the null and alternative hypothesis and see if it agrees with the printout we just looked at. All right, so we're testing the slopes, remember, in the log odds. We're doing all this on the linear log odds model. So we've got this log odds model that, I guess we don't have it anywhere, we should write it here. We have the log of the odds. Remember, odds are p over 1 minus p, so that's our predicted log odds. P over 1 minus p is equal to, and this is from the previous page, negative 17 plus some slope, which is about 2 times gender, 2.015 times gender, and that's coded as, for males, we coded it as 0, and for females, we coded it as 1, plus, so that says females, we're going to test whether that's significant, whether it looks like females have an advantage, but is it significant, or is that not such a big slope that it's just due to the luck of the draw? Plus 1.66 times the biological science score. And that's a quantitative variable going from 0 to 15. Now, we're going to test these. We know at least one of those is significant, maybe both. Let's start with the gender. Okay, so we're going to test them individually. So our null hypothesis now is about the gender slope. And the null is that this one's 0. In our sample, this is we got this. But in the population, it's 0. We just happen to get, this is small and just due to the luck of the draw. You're not going to get exactly 0 every time you take a sample. This is only 55 people taken out of a much larger population. And in the whole population, we happen to choose some girls who got into medical school more likely than, more than the average girl. That's all. These girls, that's just by the luck of the draw. That's what the null says. Then in the population, the slope for gender is equal to 0. And the alternative is, The reason we got this big a slope, strongest slope, is because it's non-zero in the population. That's why our sample, that this is a big, that this is not small and just due to the luck of the draw. It's this would be, that there is a non-zero, that there really is an advantage to girls in the whole population and not just in our particular sample. And why did I say not equal to? The way I phrased it would have been would be beta for girls should be greater than 0. That's the way I said it. I said this is an advantage that exists in the whole population. That's because I looked at this first. And then the next time I do it, I would have a greater than equal sign there. But let's think back to when we first did this. We didn't know. I didn't know which direction it would go. I didn't know that it was going to. I'm just wondering if there's an advantage to either being a boy or a girl. I don't know which direction it was going to go to. When I first did this, I really didn't. I thought it would in fact, I thought probably it would go to boys, but I wasn't sure. Because I know that there are a lot of, maybe it's an advantage for girls to get in. I didn't know, I just wanted to test it. So that's why I have the two-sided alternative here. Now, if I was going to do further work on this, I'd probably think, there's pretty strong, I'd think, well, maybe I'd have a one-sided alternative. All right, so what do? We compute a z-statistic, and we take our observed slope, like we always do, minus our expected slope, which is 0 under the null. And you divide it by the standard error for the slope. Now these standard errors are complicated to figure out, so we're just going to read it off the printout. So our observed slope is 2.015 minus the expected of 0. We can cross that out. And then the printout here just gave us the standard error for the slope, 0.8579. And that is equal to 2.348. That's what we got right here. That's our z-score. And the p-value here is 1.89%. Let's just make sure that it agrees with what, so that's the z-score right there. And 1.89%, so how would we get that? Well, what we're saying is that this is the sampling distribution of the slope under the null when there really is nothing going on. And it's distributed, we're approximating it by a normal curve. So this is our z-score, this is our z-axis. And in terms of slope, we expect 0, 2. Now, we want to know how far we got this we got about a slope of about 2. And we want to know, is that big, way out here, or is it small? I mean, how unusual would that be under the null? And the typical sampling error when you do this is given by this. So it turns out that's pretty big. So, okay, so here's our z. 1, 2, 3, negative 1, negative 2, negative 3. So 2.348 is about here. That's a z of 2.348. And that's what our slope of 2.015 translates into. So we see it's quite big. And it's going to be a very small p-value. The likelihood of getting that just by the luck of the draw is very small. This would be for the one-sided. For the two-sided, we say as extreme as that or more extreme in either direction. So between 2.348 and negative 2.348. Okay? So if we're doing a two-sided, it's probability of getting it. We didn't know which direction it would go to. So it's probability of getting that extreme of favoring of one sex or the other. The probability under the null would be that area, would be the area in the tails there. So we'll just look that up, and I did in the back of the book. 2.35 translated to 98.12%. And so, so our p would equal 100% minus 98.12%. That's somewhat of an approximation, and that's 1.88% for the two tails together, about 2%, which is very similar to what we got. So these are two-sided p-values that are given. And that makes sense. For gender, I don't think it really makes sense for biological science score, because we're pretty sure that, that it's going to be positive slope. Aren't you? Does anybody here seriously think that it would have a negative slope? That would mean the better you score on the MCAT, the less likely you are to get into med school? That doesn't even make sense. So we'd think that it would be a one-sided test, but they just gave the two-sided p-values. Do you want me to do it? I mean, I could do it. So this is for the gender. And we do exactly the same thing for the biological science score. We'd say H naught is that in the population, the slope is 0. But here our alternative, I would say, would be a one-sided. that it would be greater than 0, because the higher you get in your MedCat, the more likely you are to get into. Because we know the slope's going to be positive if it's anything. Okay, so I mean, we're just trying to look at this, we're just trying to get an estimate of how strong an effect it is here, not which direction. We pretty much know it's going to go in this direction, we just want to know how strong it is. So then we do the same thing, we'd get a z-score here of what? Z equals 1.66 minus 0 over the standard error, which is, the standard error is pretty small, 0.4629, so we get 3.5, a stronger effect here, no surprise. And then we do the same thing. And between, now we're going to get a much stronger effect between 3.586 and negative 3.586. I looked, is 99.968% approximately. So if we wanted to do, and that's where as a slope, the 1.66. The 1.66 is a stronger z-score because it has a much smaller standard error. That's where 1.66 is, right? And that little p-value is what? That's 100% minus 99.968% divided by 2. Okay? So that little area is 0.016%, and that's our p-value. But it's one-sided, so it will be double that in the printout, probably, because they gave two-sided, and it is. It's about double that. Any questions on that? Okay. The nice thing about these two-sided tests for 5, is they translate nicely into confidence intervals, because a confidence interval is always sort of equivalent to a two-sided p-value. Let's look at that here. Confidence intervals, and we'll be done this last page, and then we'll be done, and the homework's posted, and your practice exam is posted, so you know what you have to do. So let's just finish this up. All right. So now we have these confidence intervals for slopes and the odds ratio. All right, so now what are we doing here? This was what was given to you in the printout. So what's happening? Okay, so you have right here, this is for your log odds equation, right? You've got these slopes, and you have this standard error. So if we want to build a 95% confidence interval around this, we'd say what? This estimate plus or minus 2 standard errors. But instead of 2, this is a more exact critical value, this 1.96. Why? So what is this? This right here is the critical value of Z for 95% confidence interval. We usually round this to 2. This is so easy. You should know. This is really not hard at all. We've done this many, many times. All right, so all we're doing is we're saying a 95% confidence interval. So between what two values of Z, between what Z and its opposite, so between negative 1.96 and positive 1.96, 95% of the curve lies. So this right here is 5%. 2.5% on this side, and 2.5% on that side. Sorry, you can't see this. 2.5% there and 2.5% there. That's 5% together. 95% and 5% in the tails. All right? So that's the same thing as an alpha significance level for a one-sided test of 2.5% or for a two-sided test of 5%. A 95% confidence interval is similar to a two-sided significance test, with a p-value of 5% or less. Okay, so now we're going to build these confidence intervals. So how did they get these confidence intervals, for example? Well, we can do it. This is just going to be 2.015 plus and minus 1.96 times that. That's these endpoints. All right, so let's do it. Okay, a 95% confidence interval for the population slope is the sample slope plus or minus 1.96 times the standard error of the slope. Notice, first of all, that these don't contain 0. 0 is not in our confidence interval. Our confidence interval means what? That we can be 95% confident that the true population slope is contained in this interval. And since it doesn't contain 0, that's like rejecting the null. This is equivalent to the two-sided test giving a p-value less than what? 5%. And then to build confidence interval, okay, so this is for the log odds, but it's more intuitive to build it for the odds. So we have to exponentiate each side, so we find the endpoints of a confidence interval for the slope, like here, and then you just anti-log both sides. Right? So we can do this. We can make sure we get the same thing as that. So we'll just do it. All right. 1. What are we doing for the gender? Okay, so you can't do it directly. Pretend we didn't see this. All right? Just pretend we didn't have that. So a 95% confidence interval. So what are we doing? We're just saying the 95% confidence interval is going to be equal to what? 2.015 plus or minus. Usually we do 2, but why don't we make it agree with that? So we'd say 1.96, usually we just round, times the standard error. .8579. And okay, and when we subtract 2.015 minus twice that, or 1.96 times that, we get 0.331. I'm just copying from here. I assume we have to get that. And then all the way up to, we're just adding 1.96 times that, and we must get that. So that's our confidence interval. And then once we get that, what do? We just, our second step, the 95% confidence interval, this is for the slope, right, in the log odds. But now we want it for the odds ratio, which is equal to e to the slope. So we have to anti-log both sides, which is equal to e to the 0.331 to e to the 3.696, that, which is equal to 1.4, I did this before I got here, to 40.29. Okay, this means we're 95% sure the odds for females getting to med school in this model are between what? 1.4 to 40.29, greater than the odds of men getting in. How would I check that? Do you remember how I would check it? I could check what? What's the odds ratio for slope? The odds ratio for the slope is what? We did it before. Where do we have it? The odds ratio for the slope is right here. The odds ratio for gender, we did it right here on page 128, is 7.5. It's just e to the slope, right? So we're just putting error bars around that. Now the error bars aren't symmetrical around 7.5. They're symmetrical around 2.015. But remember, it's the this is not the arithmetic mean, but the geometric mean. So if we wanted to check, if I wanted to check that that's correct, I would check that the square root of 1.4, the geometric mean, times 40.29 is equal to, check what? It's equal to 7.5, is equal to the odds ratio, is equal to e to the 2.15, which is equal to 7.5. So we can check that if I have my calculator. Make sure it is. Make sure I copied it down right. Okay, so I have what? Second, I have the square root of 1.4 times 40.29. Yeah, it's pretty close. All right, so that's good. Now, let's do an eye clicker. So get out your eye clickers. And I'll show you what it looks like. And then we're going to get out early. We'll get out in about 5 minutes. Okay, so the two-sided p-value for the gender slope in the log odds equation is less than 5%, right? That was on page 132. It was way less. We saw that it was what? 1.89%. So we can conclude that a 95% confidence interval for the gender slope does or does not include what number here? This is for in the log odds equation. So just choose one of these. Now we're talking about just in the log odds equation, the slope. We're not talking about the odds ratio here. We're talking about the slope, a confidence interval for the slope. It's the first thing we did. It's this slope that the one that's given to you. The confidence interval is actually given to you on page, the one we just looked at on page 134. That confidence interval. All right, and so did everybody choose, make a choice? All right, you all done? So let's see what you chose. Good, that's right. Does not include 0. Remember, the null is that that slope is 0, and so does not include 0. Okay? That was what we're testing, the null. So when we say that it does, when it does not includes 95, it's just a picture we drew and etc. Okay, so now let's go to the next one. And now we're asking a question about the odds ratio. So this one, all right, the two-sided p-value for the gender slope, right, was less than 5%. So we can conclude that a 95% confidence interval for the odds ratio for gender No, we're not talking about the slope anymore. We're talking about the odds ratio, the one we just computed. The one we just computed. You can look at it on what we just got. We filled in those blanks, and we just got the endpoints. What would you conclude here? I'll just go to 1 minute and choose one. Of these. Okay, so I'm going to stop it now, and let's see what you chose. Okay, so you're not sure about this one. The correct answer is D. Let's see why. And rejecting the null that gender doesn't affect acceptance is the same as a 95% confidence interval for the odds ratio, not including 1. The odds, if gender doesn't matter, the odds ratio is just going to be 1 to 1, right? Doesn't that make sense? Remember, in the log odds, 0, the probability is 50-50, the odds are 1 to 1, and the log odds are 0. So if gender has nothing to do with it, then, which is what the null says, then, and you reject that, so you're rejecting that the log odds are 0, you're rejecting that the odds are 1 to 1, and you're rejecting that there's a 50-50 chance of, between males and females getting in. You're saying, no, there's something going on here. Gender does influence it. Okay. So let's go back to let's write that down, and let's go back to the document. Cameron, just finish up. All right. So let's just look. Do you see? This did not include 1. This doesn't include 0, right? And this doesn't include 1. If this did include 0, then e to the 0, then when we exponentiated that, e to the 0, which would be 1, would be included here. All right? So maybe I should write that here down here. The slope in the log odds equals 0 means that the odds ratio is equal to e to the slope, which would be equal to e to the 0, which would equal 1. So when 0 is not in the slope, that's the same thing as 1 not included in the odds ratio. If it was included, we wouldn't be able to reject the null, because the null says that there's 1-to-1 odds. It doesn't matter, right? I'm just explaining the iClicker further because so many people got it wrong. So the null is what? That gender does not, that slope was 0. So gender does not affect acceptance. This is just how you could think of it intuitively. So males and females have the same odds, right? Gender doesn't. So the odds ratio should just be 1. That's odds ratio equals 1. 1-to-1 odds. Okay. So, let's see. How about if we wanted to do an odds ratio for the biological science score? What would that mean? That the odds, well, first of all, let's just do the same thing. So what are we going to do? So we say 1, the 95% confidence interval. First, you're just going to figure it out. You have to figure out these standard errors are for the log odds equation. So you have to figure out the log odds first. For the slope, 95% confidence interval for the slope in your log odds equation. That's what you have to do first. For the slope and log odds equation, because that's where you got the error bars. That's the linear equation that you've got the standard errors for. So that one you have to figure out first. So that's going to be your sample slope, 1.66, plus or minus, since it's 95%, we're going to do a little more exact than 1.96 times the standard error here, times 0.4629. And then you get this. That gives you this. And then the next step is just to anti-log that, right? So that gives us, those limits that you see here, 0.7525, comma, 2.567. That doesn't include 0. That agrees with this. If our p-value is less than 5%, by definition, it means that for a two-sided t-test, it translates into a 95% confidence interval that doesn't include 0. The null was that these slopes were 0. We're rejecting that. So our 95% confidence interval does not include 0, because the null was that these betas were 0. These were 0. And we're saying no. 95. They're not. That's exactly the same. That's just exactly the same as getting p-values less than 5% here for the two-sided. For the one-sided, if you were doing one-sided, then we'd have 1.65 here. We'd have a 90% confidence interval. 95% means we're more short. We have a bigger confidence interval here that it doesn't include 0. Okay, so now that's what we've got here. But now when we exponentiate these, if 0 was in there, e to the 0 is 1. So now it means that it doesn't include 1. The odds wouldn't include 1. And we can see, so the odds won't, for the odds ratio, it's not going to include 1. 95% confidence interval, not for the slope and the log odds, but for the odds ratio, is equal to, and then you just exponentiate those two. So you get e to the 0.7. That's what it is. And when I did it, I got, I'll put it down here, 2.12. See, the lower limit's 2.12 to 13.03, and that does not include 1. Now, if you wanted to check, what would we check? We take the square root of 2.12 times 13.03. It's the endpoints of the geometric mean. You can see it if you take, because look what we're doing here. We're going to get e to the arithmetic mean of those two, which is 1.66. See, it's symmetric in the log, which means it's symmetric there, but it means it's the geometric mean here. So we should get e to the 1.66, which is equal to 5.26. And if you do that, you will get that. I checked it. All right, and I think that's pretty much it. And I'll see you next time. You know what you have to do. And next time we're just going to go over the practice test that's on Lawn Capital.